Hi everyone, this is Paolo AI, your AI teacher for JEPA. And in this tutorial, number 3 of the series, we are going to explain a little bit more of the details for training a world model with JEPA. So in the previous one, we sort of stopped at a very simple two-dimensional blob scenario where we were able to measure the train loss, validation loss, and the variance for the for the latent space to make sure that the model wasn't cheating, e.g., wasn't collapsing. So if we go back, just a quick reminder on the architecture. So we have X, Y, which were the two-dimensional blobs. We had the encoders. We had the prediction module. We had Z that we play with different dimensions. We didn't have an action because that wasn't necessary, so it's not an environment where we interact with the actual blobs. We had D, which is the cost function. Sorry, is the prediction cost to be accurate. This is the function that measures the prediction error in the latent representation space. So this cost is minimized during the training phase, which is essentially it was the MSE, minimum square error. We didn't use C, so I'm not sure if I might have mentioned it, but C is the surrogate cost or task objective, and this function represents a task-specific objective or cost, usually during planning and inference. So it kind of usually measures the divergence between the predicted future representation and the desired goal state. So in essence, D ensures the model is accurate, but C is optimized for a planner. And typically what I've seen is the planners are things like MPPI, which gives you the best sequence of actions to reach that goal. So yeah, in our case, we don't really have we only have D, but we don't have C and A, which are kind of related. So what are we going to do differently in this case? As I mentioned before, we are going to first of all, we're going to have 3 data sets. So blobs, moons, and circles, which are the kind of very classic examples in machine learning. We're going to use the usual validation, train, validation split. We're going to use different seeds. We're going to use the same budget for all runs, so we are not going to use more or less compute. And for the held out data, because well, you can do the same thing in classic machine learning. I'm also going to use this 5 NN accuracy latent space. And also, just to add a little bit more complexity, I'm going to lift the two-dimensional space into a higher dimension, so to make it harder for the predictor and the encoder to kind of learn this representation. Otherwise, two-dimensional is too easy. And we're also going to try to change the CILU, so the activation neuron, to a ReLU. And because I've seen that in the paper, sometimes they use one or the other one. They say it's a little bit better. I just want to see if there is any difference really. Okay, so that's the explanation. What I'm going to do here, we have all the configs. So we have 3 data sets. We have like several dimensions for the latent Z. We have activations 2. We have 3 seeds. There are 1,800 samples. I got batch size of 192. I don't know why. You can change another one as long as it fits into memory. I went for 140 epochs. And patience, well, it's not something that you find in the papers. It's just like, it's just really a counter. If it takes too much to train, there is a clock and like it just stops. We have the learning rate, the weight decay, tau, the noise standard deviation, and the test size, okay? Plus the validation size within the train split. And this is the KNN neighbors set to 5. So essentially, if I want to see if the model is able to distinguish between blob A or blob B, it's going to take the 5 closest point, and is just going to kind of measure within that distance. Okay, and let's see. I mean, this is all kind of obvious. So let's load this. Okay, so the configuration is loaded. It looks fine, and is using CUDA, so it should be faster. I forgot to do that before. And then, well, we're using some basic functions here. So we are setting the seed. Okay, so we are using a fixed seed, so we don't get, like you can replicate this. We use two different names for the activation functions. The lift features essentially takes the two-dimensional problem and lift it into higher dimensions. So for blobs, I do these 4 operations. For moons, I do a little bit more, and for circles, I do a little bit more. And then I also add some noise. I can then build a data set. Okay, so I make blobs, moons, circles, this noise factor, the number of samples, and the random seed. Then I lift them into a dimensional space, and you get the results. Split and scale, this is it's the really standard process. So I have train, validation, and test. And the mean and the actual scale, so how far did it, the range essentially. And then I'm just going to plot them in 2 dimensions, of course. So in 2 dimensions, I have the original view, so 2 dimensions for the blobs, moons, and the actual circles. So these are the kind of very common ones, and of course I cannot visualize them, but I sort of lift them into these extra dimensions. So yeah, as I mentioned before, in terms of the original diagram, just as a reminder, so X was the view A, so it's actually the training batch that is fed to the context branch. Y is the view of B, so it's fed to another branch. So we split, we take the original point and we split them in 2 views with some noise. Then we have the encoder, so we have for X and Y, we have the predictor, which is no condition on actions, it doesn't make sense. We have the Z, which is essentially the latent variable, and we have the cost function, which is the mean square error. And the C, really, it's like, as I mentioned before, it's not really, like, we don't really need that. It doesn't make sense, but is essentially, well, the way I say it is the validation. It's the kind of the validation JEPA laws for the checkpointing. Okay, so everything is implemented in this class. So I try to label them. So you have the encoder, you have the for X, the encoder for Y, which are basically using the same structure. Then we have the predictor. So yeah, there is no action as well. And this one is using the latent dimension. And then we have the gradient, right? Which is, once again, is essentially like the one that you calculate between the context and the target encoder. What else? This is the EMA as before, and we have the forward pass. Make 2 views is essentially the same function that separates those points into 2 points. So you have 1 point separated into 2. And then we also measure the evaluation loss. Okay, so this is essentially very similar. So, we have split those training set, and then like from something that was not seen or trained before, we are going to essentially recalculate the kind of losses. And encode NumPy, well, this is just a utility function. Okay, so then we're going to train one configuration here. So this is just like a function to create the predictor. We attach the optimizer, okay, with the configuration we decided. So we have the learning rate and weight decay. Okay, so those that we defined before. We create a train component. Okay, we want to essentially make sure that we are following the trace, validation trace, and the spread trace. And I also start a timer so that if these things takes too long, I run out of patience and I stop that. And then yeah, for each epoch, we do the train. We take the the two views, the x and y. We do the encoders, so we calculate the s, calculate the loss, and then we do the optimizer backward. So you do the backward pass, forward pass, and essentially train that. Then each 5 steps, each 5 epochs, I basically plot also the validation loss. And then I use that, if you remember, there was like that let's call it safety check. If it's less than a certain small number, I essentially sort of keep that as the best state. So it's just a way to essentially measure, track the validation loss. So whichever is the lowest one minus some small difference, I'm going to keep it as the best. And then okay, I take the last one, so the last train loss, the last validation loss, the last test loss. I compute all the latents for the train, validation, and test. And then I create this k-neighbor classifier, which is set to 5. And I use that to, I fit it between, very importantly, between the Z and Y. So keep in mind, this is kind of an idea I had. I've not seen it in other papers, but essentially, I want to see if within the representation in the latent space, using a very simple, let's say, unsupervised classifier like k-neighbors, is able to find the same points within the labels, because we have two colors, two classes. In theory, if he was able to separate these two things, he should be able to distinguish them with a simple neighbor classifier. So essentially, I kind of apply that, but as you can see, is on the Z train, and Y train. Well, that's essentially, well, it's calculated up there, but is essentially the label, and then I'm going to predict it, and I'm going to measure the accuracy. Okay, so this is defined and not any errors. The first thing I do is a very simple smoke test to kind of see if things are working. I got stinged many times by that, so I just take the moon dataset with a zero activation. The latent dimensions are 4. The input dimensions are 8. This is the best epoch, so 115 from that one. The train loss 0023, validation loss, test loss, latent spread to see if it's collapsing or not, like Nutella. The test accuracy for K and N, which looks good, I think, and the runtime. So how long did it take? And the split sizes, so like it was train, validation, and test. So I sort of split that way. So yeah, that looks good. Obviously, this is interpolated, so but this is the validation JEPA loss that goes down. It looks good, and this is the train loss. That is a little bit of a zigzag, but it seems good. Okay, so now we do some checks just to see if, for example, well, the test accuracy for KNN should be between 0 and 1. That's happening. The latent spread, well, should be more than 0. That's happening. There shouldn't be any infinite numbers in the Z test, just to make sure there's no craziness happening there. What else I was doing? Yes, if the input dimension equivalent to the observed dimension, and well, the best epoch should be within the real epochs. And yeah, this is the total observed, which is train, validation, and test. Okay, so hopefully, like quick smoke test, looks fine. Then we have a function to aggregate results. There is nothing fancy here, but I essentially take all the various losses. So I do the mean standard deviation, spread standard deviation, runtime, mean, best epoch, mean, etc., etc. And I also save them because I want to use them in the next tutorial. So hopefully, I'm not sure how collab works, but yeah, I just want to make sure I can use them in the next tutorial. And really, this is just kind of looking at the results. I mean, there is nothing fancy. So saving checkpoints, and then I do some visualization. Okay, so let's run this. And so what we see here, we have 90 epochs for the blob example. And I'm using essentially, sorry, it's the configuration, not the epochs, but I'm using blobs with the ReLU dimension of latent equal 1. That's the seed to apply some randomization. This is the test accuracy, and this is the test loss. Okay, so I run this, so it's like it's very simplified to give you a good idea of what's happening. Okay, and then okay, lots of charts to explain. So yeah, so as you can see, all the configurations until 90. So the last one is with circles. We have a CLU with Z dimension, equals 16. And we have this nice test accuracy, 0.99. So they kind of look good. I mean, some of them are terrible. I can see already some 60% here. So yeah, so this is kind of interesting. We have the final results here. So we have the best checkpoints. Okay, and we have these three main charts. Okay, so how we are going to interpret those? We have on the first column the held out JEPA loss versus Z. Okay. In the middle column, we have the test for the 5 nearest neighbor accuracy versus Z. And on the right column, we have the latest spread versus Z. Okay. Excuse me. So we also compute. So we have the held outs. So blobs, moons, and circles. Okay, so on the rows, and then we also calculate the kind of Silus minus ReLU effect sizes. So we are not just kind of looking at two lines and guessing. We are just measuring the actual delta. Okay, so let's look at blobs. You can see that in terms of performance, it sort of saturates quickly. So like if we look at 4, I mean, we already get very quickly to 100%. So we have the ceiling. So having a very large latence doesn't bring any benefit. And the spread, it's kind of started, 0.5. It goes up a little bit. It's very high at the beginning, which I believe is expected. And then it sort of stabilizes for higher dimensions. But really, since we are like if you're 4, we're already decent. We're looking at this kind of spread here. So that's for blobs. For moons, this is kind of interesting because moons have the higher, if you remember, so moons had a higher dimension. I was kind of expecting to have a higher Z. And so we can see that the loss takes more time. I mean, the loss is lower for higher dimension. So so essentially, like you need something around 8, which I believe was peak here, because while it's I guess it's a more complex set to distinguish. And if we look at the circles, it's kind of learning, so the loss is still going up, but in terms of accuracy, it's kind of surprising. It's really good at 4, but I was expecting it to be at 8. But I think 4 is already very close to the best, right? So that's why my approach picked 4, which is very interesting. And the spread, well, it's sort of, a lower dimension is very high, which means it's probably collapsing. But when you look at 4 or 8, yeah, it's still kind of low. But the 16, which is the true dimension I lifted this, it's higher. So yeah, so I think if you look at these ones, it kind of the spread kind of models the complexity. So Moon had 8 dimensions, so I was kind of looking at here, and for the circles, the spread is higher here. But it's sort of match, yeah. So we know that, yeah, this was 4-dimensional, and 8, the moons was 8-dimensional, but circles was 16-dimensional. If we go back here, if you remember that, for the circle, the concentric circle, it was 12-dimensional. So I was expecting something like 4, 8, 12 for accuracy, but actually it isn't. And I wonder if this is something to do with symmetry or something like that, that the latent actually doesn't need all those dimensions, which are, I mean, obviously they're calculated. So like with 4 or 8, it does bring you a very good accuracy, although the train loss, the kind of loss, was still going up, which is interesting. But the spread, it was like very, very big at the beginning, and then it sort of went down, like sort of a 4 looks like a good point. I would say 4 or 16, they look actually very good in terms of spreads for this one. And they all kind of go to 16. So if you choose Z to 16, you have like a very good spread, but then of course you also have to look at the accuracy. So below this, I also measured the actual ReLU versus CILU, just to kind of show if there's any difference. So for blobs, the best mean accuracy is at Z16 with the CILU activation, and the smallest Z with 1 point of the best is at Z4 for ReLU. The mean CILUs minus ReLU accuracy delta cross is 0.015, and that's for the moons, and that's for the circles. So essentially, what's the takeaway here? I'm trying also kind of understand this. So I think, I mean, in terms of interpreting these charts, if you look at the held out accuracy, if Z rises, the bottleneck was too small, right? So you have to kind of take a look at the held out JEPA loss, and then you have to check the latent spread to ensure that you're not buying low loss with a collapse representation. So you have to always check them in parallel, and then maybe only after that you can compare the ReLU and CILU by effect size. So I think for me, the takeaway from this tutorial is choose the smallest latent size that gets you within roughly 1 percentage point of the best held out result. So the idea is you want to have a competent representation without paying like a really high performance penalty. So I mean, for me, like looking at these results is don't take the biggest don't always pick the biggest latent, and don't always use silos. So the real lesson is, the complexity determines how much compression you can get away with. Make sure you compare the dimension versus the spread, the kind of accuracy for your downstream task, and the just the pure loss. Kind of see what's going on with the dimension, and I think, well, I mean, the activation mostly matters when capacity is tight. So like if you have a very if you have a very small if you're saying, hey, I just want to, I have zeta equal 4, tell me which one is the best, right? I just want to fix zeta to 4, and I want to find the best one, right? So like, should I use a silo or a relu? I think that's the way you should approach it, rather than just like choosing one always. And so so I think, as I said before, so like the takeaway is, if the data gets more structured, zeta is to grow, but it usually only has to grow to the point where performance saturates. And the silo helps mainly in the more constrained settings, rather than like having a massive impact on that one. And so feel free to play with this notebook, and try different settings. If you have any other ideas for making better estimates or datasets, let me know, and I'll see you in the next tutorial, which is about inference. Thank you for listening.